All right, today we're going to be doing Unit 2, Lesson 3, which is going to be polynomials of a higher degree. In our beginning lessons, we learned about quadratics, which were degree 2. Now we're going to do degree 3, degree 4, degree 5. We're not going to necessarily get into the specific names, but it's more of the algebra. Anytime we have higher degree polynomials, if you have to do things by hand algebraically, we're going to need a method to bring them down. For the most part, the lowest level that you would have to do by hand will involve quadratics. So that means that somehow we have to be able to take what we have and break it down into quantities that involve quadratics, so you can factor, use quadratic formula, etc. Higher level polynomials are solved with advanced algebraic methods, which we're not reviewing. Okay, we're not learning all of those methods. A lot of them are computer generated. So we're just going to get them down to simpler polynomials such as quadratics. Okay, so if we take a look, first thing is definition. The graphs of polynomials, they are both continuous and smooth. What that means is that when I put my pencil down to draw them, or my marker, and I go to draw them, they are curves I can draw without picking up my pencil. There is no break in the graph. So they don't look like piecewise functions. They're like super roller coasters. They move left to right through the graph. Okay, page 103 in your textbook are more examples of those if you want to refer to them. Now, the simplest graphs are what we call monomials. They have one term involved. And we're going to link this to what we already know. So, here's what I mean by that. If I say, in general, sketching, this is the graph of y equals x squared, it is U-shaped. If I know, and we did this before, y is equal to x cubed, okay, we have basically two parts. We have this part that looks like part of a parabola, but then it switches direction and goes downward in the opposite direction. Everything we know about polynomials, we can kind of extend back to these two definitions in terms of what they look like. So when I look at the slide that I have up here, if n is even, so that would mean n would be 2, 4, 6, or 8, it's going to be U-shaped. U-shaped. And I say that in quotes, and you'll see why in a second. However, if n is odd, it's going to be similar to x cubed, where I don't have the n direction going the same. Got opposite directions. Okay. As n gets larger and larger, so this might be x squared. If I go to x to the 4th, my dotted line, it's still U-shaped. It's just that down here at the vertex, it's much more flat. So that's something that we can also extend to our knowledge of what the graphs would actually look like. Okay, now we're going to talk about what's called the leading coefficient test. If n is odd and the leading coefficient is greater than 0, oh, this sounds really, really complicated. Let me erase the x to the 4th example so that we don't confuse ourselves. Keep these two here. N is the leading coefficient. Do you know what the word coefficient means? I forgot to ask you that. Of the x squared term, whatever the highest power is, the leading coefficient. All right, so if n is odd, is it going to look like x squared or x cubed? If n is odd. Let's understand that definition part first. It's going to look like a cube, okay? If the leading coefficient is greater than 0, in other words, it's positive, that's the math definition of positive, that means it's going to model off of what we already know for x cubed. It's going to rise to the right, and it's going to fall to the left. However, if the leading coefficient is negative, like if it says negative 2x to the 3rd, for example, it's going to flip around, and it's going to rise left and fall right. New words for something you already know. Okay, so for example, f of x is positive x cubed versus f of x is equal to negative x cubed. Remember, the negative out front creates that flip. We're just describing the end behavior. We're describing the arrowheads, basically, using the leading coefficient test. Now we can switch over if the degree is even. So now this is going to be positive x squared. This is going to be negative x squared. So notice n went to a positive. We're now going to think about our graph of x squared parabola. If the leading coefficient is greater than 0 or positive, what do you think the end behavior is of these two arrows that I'm pointing at? Using the word rise or fall. What are they doing? Both rising. Both left and right rises. And if it's a negative out front, then the parabola opens down, which we already know, and that means it's going to fall left and fall right. All right, so let's talk about what we really just went over because it's not new information. The only thing that's new here for us is that in the first couple lessons, we only talked about x squared. Now we're extending to x cubed, and we're going to talk about x to the fourth, x to the sixth, x to the third, x to the fifth, x to the seventh. We're able to take what we know and extend it beyond. So here's an example of that. What just happened? Yes, that just happened. We just took basic functions and we ramped them up. So notice, what's the degree in A? 3. So that means n has a highest value of 3. It's going to model out off of x cubed. It is x cubed. And if I look at my leading coefficient, how would you describe the end behavior? What's going to happen with the arrowheads to the right and to the left? If this is positive 2. It's going to rise right and fall left. It's going to look just like this graph because this is a positive 2. All right, is there anybody that's lost or has no idea why I got that answer? What about the next one? Negative 4x squared. This one should be super easy. What's the end behavior based on the leading coefficient test? Both fall. Left and right fall. It's going to be a U shape because it's an even n value, but then it's going to fall downward because there's a negative out front. Okay, so that's the first part of this lesson. Okay. Next up. A zero, by definition, this is a new vocabulary word. You need to highlight it. You need to know it. A zero is the x value when f of x equals 0. F of x stands for which letter? X or y? Y. Okay, so now take a look. I'm going to replace this with y is equal to 0. What do we know about all locations in the world that are y equal to 0? That's a definition of when y is equal to 0. Take a look. What do we know always has y equal to 0? X-intercepts. So then we're going to connect this to the idea of x-intercepts, which are the same thing as zeros. They're synonymous with the word 0. Now, this ties in, this is a very formal definition to the fundamental theorem of algebra. If a polynomial is degree n, so for example, if I have f of x is equal to x squared, the highest power of x is 2, which tells me there are 2 solutions. If this was an equation, there are 2 zeros. There are 2 x-intercepts at most. It could be less than that, it could be 1, it could be 0. The other thing that we know is that if there are 2 of them, that there's 1 less maximum or minimum. Think about the graph of x squared. If I have 2 endpoints, then I can only have 1 minimum or 1 maximum depending if it opens up or down. So it's always one less. And then we get this definition. Take a second to write it down. Think about it. Do you have this there to fill in? Okay. So fill in your slide. I'll give you a minute, and then we'll talk some more. Okay. Part 3 is the most important new information, definition-wise, in this lesson, moving forward to do everything else in the lesson. Okay? So we really need to understand what this says. Okay? And here's what it says. If A is a real number, and f of A equals 0. Okay, so here's an example. If I plug in 3, so this is my A value, 3, what do I get into f of x? 0. If f of A equals 0, do you agree that this yields the ordered pair 3, 0? Is everybody with me with that? Like just in terms of function notation, right? Notice 3, 0 visually is the x-intercept. 3 is the 0, 3, 0 is the x-intercept. Okay? And here's the connection you need to make. That if this is the value of 3, then in my original problem, I had an x minus 3 as the factor. You say, that's a factor? What do you mean by that? Well, if I take this and turn it into its intercept form, does it make sense that this and this are connected? They're the same thing. That idea that I just wrote in purple, here, and connecting this piece is exactly what is the explanation for part 3. All right, is there something that I said that sounded weird or doesn't make sense? Process, ask anything you want. Okay, what are you confused on? Can you be where you got lost? I gave you a random example for this. I chose x squared minus 9 as my function. And I said, if you come along and choose a value, so I chose 3 for my a value. When I plug 3 into here, I get 0, correct? Okay, that's the first part of the definition. If f of a equals 0, so f of 3 equals 0, okay, then you have two things that happen. Number one, this is the ordered pair that's on the graph based on this notation. Okay? 3, 0, anything that has a 0 for y is always an x-intercept. Doesn't that connect to what we know of the graph of x squared minus 9? And then from here, I said, okay, the last part of this, the extension piece, is the fact that if I know I have an x-intercept of 3, x minus 3 is the factor. Because if you set x minus 3 equal to 0, that yields 3 as the 0. Right? 0 is when y equals 0, and then you would solve the equation. Got it? Okay, moving on. I'm going to just stand in front of here and go through all this real quick. Okay. Example 1, find all the real zeros. Fantastic. As I promised you, we're now going to ramp it up. So now we're not getting just quadratics, now we have higher order. So the first step is going to be you have to be able to break it down. How do we break down x to the third plus 10x squared plus 25x? Okay. Factor out an x. So we're going to use simple algebraic methods. Then what? How can I keep breaking this down in order to come up with all the zeros? What? Factor x plus 5 plus 5. Okay? So if I were finding all the zeros, f of x gets replaced with 0. I'm solving this resulting equation. It is not a quadratic equation. It's higher order than x squared. But I'm breaking it down into things that look like x squared, the methods we've used. So what do I get for my x values? 0 and negative 5. Now students always ask me this question. Mrs. Gomer, on the previous slide it said the highest power told me there should be 3 solutions. Well, this is a perfect example that there are 3 solutions, but one of them counts twice. Which one? Negative 5. You've been calling these double roots in the past? Yes? You've heard of that, double roots? All right? We also could call this negative 5 and 2. Where the m stands for multiplicity. So that means that it's basically I've got a negative 5 twice. Now I have 3 answers. 1, 2, 3. Questions on that? Multiplicity of 2. Have you ever seen the movie Multiplicity? It's from the 80s. Were you even born then? Oh God, you weren't, were you? There's a movie with the original Batman, Stephen Keaton, Michael Keaton, and he clones himself to be like a mom, to be a dad, to go to work, to all this stuff. It's called Multiplicity. He was a genetic engineer, and there was like 5 of him running around trying to do everything he needed to get done in a day. That was the premise of the movie. But of course, what happens with genetics when you clone yourself? Yeah, one of them ends up being like the devil and messes everything up. That's just what happens. We won't get into the religious ramifications of cloning. All right, now, we talked about repeated zeros, but what I just went through verbally is right here on this slide. So those of you that go back or review this video, this is going to be here. I'm just going to take a second. I'd like you to read it also. In general, if you have a quantity that is repeated when you factor, okay, you can rewrite it with an exponent. So if I look up here, notice I could write this as x times x plus 5, the quantity squared. That square is the k value, which indicates the multiplicity. So that's where in the last example, when we said that x is equal to 0 and negative 5 multiplicity of 2, that 2 ties back into the k value. Okay? If k is even, something's going to happen graphically. If k is odd, we're going to have something different happen. Now, this is the new connection to graphing that we're going to talk about here. Let me show you. Okay. If k is odd, so I'm going to use the same example, x times x plus 5 squared, right? On my graph, 0 is an x-intercept, and negative 5 is an x-intercept. Remember, zeros are the same thing as x-intercepts. Okay. Let's talk about leading coefficient tests. If I multiply this out, I'm going to get 1x cubed dot 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 with stuff after it. What's going to happen for the end behavior of 1x cubed? This is the part you probably want to check in if you haven't been paying attention, because we're about to go into more complex examples. If I tell you that I have f of x equals 1x cubed, what's going to happen? What's my end behavior look like? Does it look like x squared or x cubed? Does it go like this, or does it go like this? It's my 70s disco move. Which one is it? It's going to rise right, fall left, correct? Okay, so at 0, this is going to cross. It's going to come down. Okay, my graph, so it's rising to the right. At negative 5, I have a repeated 0 that is even. So notice here, this is an even k value, which means that rather than coming back up and crossing like a parabola, it's actually going to turn around and touch and fall back down to the left. So notice this is going to be a touch right here. It does not cross the axis. Rises right, falls left, crosses at 0, which, by the way, 0 has a multiplicity of 1, so that's a cross because it's odd, but it touches at negative 5. The touch isn't because it's not just repeated, it's repeated an even number of times. Questions on that? Even number of times, yes.
How do you know to, like, when you graph it, like, how do you know to make it
Turn back around?
yeah.
Okay. Well, let's talk about a parabola. A parabola is y equals x squared, correct? Y equals x squared. Y equals x squared, when you look at the vertex down here, it's going to turn back around and come up. Rise right, fall right, correct? What I know about the graph, this may not be the exact points or locations. It might come down further. I'm not worried about the exact points in between the intercepts right now. I'm looking at end behavior. I know that it had to turn back around in order to fall. And the turnaround point is going to be at the tangent point. Tangent's another word for touching. Does that make sense? That's what we're now learning in this new lesson that we're extending to the graphs. Okay, real quickly, pull out your calculators, please. I'm going to ask you to find all of the real zeros of a very complex one, x to the 5th. You cannot break down x to the 5th. You don't have algebraic methods right now to do that. So that's why we go to this technology. Go ahead and put it in your calculator. And now we also need to extend to what we did in Unit 0. Ironically, we're finding zeros. So what information from Unit 0 can we use? Zeros are the same thing as what? Put your y equals, put it in. What are zeros the same thing as? What are they synonymous with? I say 0, you say x-intercept, 0, x-intercept. 0. Do we need to do the cheer? Will you remember? I think we need to do the cheer. Can we do it one time? One time? Okay, so like I say 0, you say x-intercept, 0, 0. Okay, now we're going to do it louder, real loud. Come on, it's like 8:12 in the morning. Ready? I say 0, you say 0. 0. Easton. Rovers. Easton. Come on. What? All right, so yes, anytime you're asked to find the zeros, in your brain, it needs to tell you that means x-intercepts. How do we find x-intercepts in the graphing calculator? You make what? y2, so this is going to be our y1. y2 is going to equal 0. and we need to find what commands? Intersections. Go ahead and do that, please. Do you have 5 of them? Are there 5 intercepts in this problem?
No.
How many are there? 1, 2, there's 3. There's 3. Let me see how many I got. All right, I got 3. Make sure you can find at least one of them. You will have to find all of them, but if you need help, I'll take a lap. Let me know if you can't find one of them. Like, I don't mean any of them. I really can't. No idea what the calculator's supposed to be doing here. You good? No. Put a note in your notes, like on the margin, just say that. Calculate menu, option 5. And then you would just on your guesses. When you're doing it, you just go through all the same commands. However, you move your cursor closer to the other zeros. All right, so I did ask you a question. The 3 answers you should get are up here from left to right: negative 1.39, negative 0.51, and 1.82. Where is the disconnect between the fact that graphically I only have 3 solutions, but I have x to the 5th? All of them cross. There's 2 possible answers here. What's the problem here? Jordan. Right, like think about the fact if I factored and I got x squared plus 7 as one of my factors, if I set this equal to 0, isn't it going to give me the square root of negative 7?
Yep.
That's not going to show up in your graph as a solution. So that's one possibility. The other possibility is that one of these is a triple root. So it would be like, say it was this one. It would be like x minus 1.82 quantity cubed. The cube, it still crosses through, right? But it only looks like it would count once. So you don't know when you have triple or to the 5th or to the 7th powers. But most likely it's going to be the non-real solution as one of your factors. This will make more sense if you're a little hazy on it right now. Let's move on to example 3. All right, so do you remember earlier I did that problem where I drew the purple and I drew the connection here, the purple, the factor, going back to the intercept form? Here is the working backwards portion of this. Write a polynomial function in general form whose zeros are negative 2, 1/2, and 0. So what they're telling you when you read this is that at negative 2, I have an x-intercept, at 1/2, and I also have one at 0. I have 3 intercepts. I don't know anything else about the polynomial except for that. So if I know those are my intercepts, can you tell me the factors? What factors would give me negative 2? X plus 2, yes? The opposite sign, x plus 2. How would I get a factor of 1/2? X minus 1/2, let's start there. X minus 1/2. And how do I get a factor of 0? Just x. Okay. Here is a function that looks like that. Awesome. There's only one problem, and you need to highlight this and make sure you don't make this mistake, and it's right here. I don't want you to write x minus 1/2. What I would like you to write is 2x minus 1. If I take the quantity 2x minus 1 and solve it, set it equal to 0, don't I get 1/2? Okay? So theoretically, I understand what you're thinking. You're just following suit and plugging in numbers. However, we need to transform it into a non-fractional polynomial factor. Questions on that? The reason why is because oftentimes when you have these problems, I'm going to ask you to give me the answer in general form. This would be considered intercept form, correct? If I have intercept form and I want to go to general form, how do I do that? What's your F word, favorite F word? Factor, right? Or refoil. Factoring and foiling are opposite operations. So I would FOIL the first two, and then I would distribute the x back. This is what I get. Yes, sir. Well, if I just move the denominator in front of x, right? Think about it. If I set this equal to 0, don't I add 1 and divide by 2, which gives me the 1/2? That's how you do it. Take the denominator and put it in front of x. All right, so I did ask a question at the bottom just to kind of run this through your brain. Is this the only solution? No, right? Do you know whether this function goes like this or like this? Or if it goes like this, or it goes down and like mountains through? You don't know. This is the simplest solution in terms of what you would need to do. What would change the shape of it is going to be a coefficient out front. And we know that from here that I've got x to the cube, so we know it's going to fall either like this or it's going to look like this depending on the coefficient. This is just the simplest. Okay, now you have a chart in your notes, correct? Flip the page. You have a chart? Yes. I would like you to take, if you know what you're doing, 5 minutes, you should be able to fill in this entire chart. I also am going to advise you to put a note at the top to study this page. And we'll see it again. Not exactly this, but it's format-wise looks exactly the same. Study this page. Okay? So, let me start you out on the first one here. On the first example, you were given a function, correct? On the left? All right. This is all non-calculator. Everything in here is non-calculator. What you need, you can get by looking at the actual function. The first thing I always want to do is, I want to look at the factored form of this, and then I also want to look at 1x cubed dot 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 f of x. I want to look at the general form. The general form is always going to tell me the leading coefficient test information. Okay? So if I would multiply this out, I would start with 1x cubed. That's what I would get. Okay? So now I can jump over here to the right, and I can say, okay, in the factored form, what are my zeros? What are my zeros? 0 and 4. So I'm going to write a 4, and I'm going to write 0 multiplicity of 2. Why did I have to put the multiplicity of 2? Because it's squared. Now, let's come back over here, because we're going to take these two pieces of information, and we're going to put them together to make our graph. If I have 1x cubed, since this is a positive one, great, purple marker's dying, I know that this is going to rise right and fall left, correct? It's going to look like x cubed, what I traditionally know, rise right, fall left. Positive 1 doesn't change that. Okay, so then I make my graph, and I say, okay, here's what I know. I know that at 4, 1, 2, 3, 4, I have a 0 or x-intercept. At 0, I'm going to put a little star by this. I have an intercept. On the far right, my graph is going to rise. Perfect. And it's going to cut through at 4. But now, because I have a multiplicity of 2, my graph is going to come back and touch at 0, and then it's going to fall. Why is it only going to touch at 0? What's even? Yes. Multiplicity is even. So because this is an even multiplicity, I know that this graph is only going to touch at 0. It does not cross through the x-axis. All right, like I said, 5 minutes. Work with your partner. We'll go to, I should be able to do it by 8:30. Go ahead through. Okay, so in example B, you were given your function in intercept form. So I'm going to go ahead and turn this into 1x to the 4th if I started out from my leading coefficient test. X to the 4th, this is even, which tells me it's going to be a u that opens up because this is positive 1. That's everything I can garner from transforming it into the initial part of the general form. Now, if I move over here to my zeros are going to be a 0 and negative 5 with a multiplicity of 3, correct? Okay, now, multiplicity of 3, this is going to be an odd k value. Okay, odd k value tells you that this is going to cross at negative 5. So if I go to my graph, boom, I come across, I've got 0, I can place that on here. Negative 5, I can place that on here. Rises right, falls nothing, rises left. So this is going to come up, this is going to come down, this is going to come around. That's what I'm looking for. General shape. Yep.
So if it didn't cross, it would look like
Well, if it didn't cross, then this would have to be x to the 3rd or x to the 5th. Because you have to change the multiplicity to an even.
So it would be it wouldn't be u anymore.
It wouldn't be a u, it would look like x cubed. Yep, good question. What do you think? Yes? We're starting to click a little bit. Let's try example C, before the bell rings. All right, so we look at example C. Now we're going to go in a different direction. Now we're going to start here. We're told the zeros are negative 8 with a multiplicity of 4. That's going to translate back over here to f of x is equal to x plus 8. That's that quantity thing we were talking about earlier in purple. Plus 8, there's the sign flip, and a multiplicity of 4 tells me that I have that to the 4th power. My general form of this is going to start out with 1x to the 4th, dot, 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 which doesn't that tell me that's a u? Could I have put a negative out front here? Absolutely. I could have made this a negative 1. It's easier not to algebraically. From here, I'm going to come in. What's the only x-intercept I can place on my graph? Negative 8. Now you're getting it. You're with me. So at negative 8, I have this. It's going to open up. But because my multiplicity of 4 is an even k value, that means I don't cross at negative 8. I actually touch at negative 8. It looks like this. Now I'm going to blow your mind here. Ready? Doesn't this mean take the vertex and shift it left 8? Same rules. All right, let's do example D. This one, even the best of you, I think I tricked some of you. Sorry. Last one. Example D. I gave you a picture. What can you tell me about the picture? X. What do I have here? I have negative 3, and I have a 1, right? Okay, but the problem is at 1 it crosses. At negative 3 it does what? So this could be a multiplicity of 2 in simplest form because it touches. This is a touch. That means that k has to be even, which I have right there. Fantastic. Now I can come over here, take this information, and translate it back into the intercept form. F of x is equal to x minus 1, x plus 3 squared. Are there any questions on that connection between the red and what I just wrote in black? Okay, there's an issue right now. Here's our issue. We never had to deal with this when we didn't start with the graph. You notice how this rises left and falls right? That tells you that in here, my a value must be negative. So I need to have in here a -1 at the very least in order to match to the picture, because it doesn't rise right and fall left like x cubed. Looks like negative x cubed. Why is that important? Well, when I come over here now and say f of x is equal to -1 x to the third, now that matches to rising left and falling right, which is what's happening in the picture. So we took a package, we wrapped it up nice, we just finished with the bow. This is the connection to everything that we've been doing, especially now with these new quantities that we're talking about.